Physics is the branch of science that studies matter, energy, motion, and the forces that act upon them. It is one of the oldest sciences, and it forms the foundation of our understanding of the natural world. Whenever you observe something moving, falling, or changing, physics is involved. For example, when you drop a ball, physics explains why it falls toward the ground. When a car moves along a road, physics describes how its speed changes and how forces act on it. When planets orbit the sun, physics predicts their motion with remarkable accuracy. At its core, physics is about discovering the laws that govern the universe. These laws allow scientists to understand not only everyday events, but also complex phenomena, such as electricity, magnetism, and even the behavior of stars and galaxies. Physics is therefore not just a subject, but a way of thinking. It helps us analyze the world logically, ask questions, and find answers based on observation and reasoning. Understanding physics begins with one essential idea. We must be able to describe the world in a precise and measurable way. To describe the physical world accurately, we must first learn how to measure it. In physics, measurement is the foundation of all scientific knowledge. Without measurement, we cannot describe motion, compare results, or make accurate predictions. Measurement allows us to assign numerical values to physical quantities such as length, time, and mass. For example, instead of saying an object moved far, we can say it moved 10 meters. Instead of saying something happened quickly, we can say it occurred in 2 seconds. This precision is what transforms simple observation into scientific understanding. Every measurement consists of 2 parts, a number and a unit. The number tells us how much of a quantity is present, while the unit provides a standard for comparison. For instance, if we say an object has a mass of 5 kilograms, the number is 5, and the unit is kilograms. In scientific measurements, accuracy and consistency are extremely important. Scientists must ensure that their measurements are reliable and can be reproduced by others. This is why standard units are used worldwide. Measurement is therefore the language through which physics describes the universe. Without it, the laws of physics could not be expressed clearly or tested experimentally. To ensure consistency in measurements across the world, scientists use a standard system of units. In physics, physical quantities are properties that can be measured. These include basic quantities such as length, mass, and time, as well as derived quantities like velocity and force. To ensure that measurements are consistent everywhere, scientists use the International System of Units, known as the SI system. The SI system defines standard units for fundamental quantities. For example, length is measured in meters, mass in kilograms, and time in seconds. These units are universally accepted and used in scientific research, engineering, and education. Derived quantities are formed by combining fundamental quantities. For example, velocity is defined as displacement divided by time, and its unit is meters per second. Force is another derived quantity, measured in newtons. The use of SI units ensures that scientists from different countries can communicate their results clearly and accurately. Without a standard system, measurements could become confusing and inconsistent. Understanding physical quantities and their units is essential because it allows us to describe physical phenomena in a precise and meaningful way. This forms the foundation for all further study in physics.
Now that we understand physical quantities and units, the next step is to explore how these quantities are used to describe the physical world more precisely. In physics, not all quantities are described in the same way. Some quantities can be fully described using only a numerical value and a unit. These are called scalar quantities. Examples of scalar quantities include mass, temperature, time, and distance. For instance, if we say an object has a mass of 5 kilograms or a temperature of 30 degrees Celsius, we have completely described those quantities. However, there are other quantities that require more information. These are called vector quantities. A vector quantity has both magnitude and direction. For example, velocity is not just how fast an object moves, but also the direction in which it moves. If a car is moving at 20 meters per second to the east, both the speed and the direction are important. Similarly, force is also a vector quantity because it acts in a specific direction. Vectors are often represented using arrows. The length of the arrow represents the magnitude, and the direction of the arrow shows the direction of the quantity. Understanding the difference between scalars and vectors is extremely important in physics because many physical phenomena depend not just on how much, but also on where and in which direction. This concept will become especially important when we begin to study motion and forces. Now that we can describe quantities with magnitude and direction, we are ready to study one of the most fundamental ideas in physics: motion.
Motion is one of the most basic concepts in physics. An object is said to be in motion if its position changes with time. To describe motion, physicists use several important quantities, including distance, displacement, speed, and velocity. Distance is the total path traveled by an object, regardless of direction. For example, if a person walks 10 meters forward and then 5 meters backward, the total distance traveled is 15 meters. Displacement, on the other hand, is the straight line change in position from the starting point to the final point. In the same example, the displacement would be 5 meters forward. Speed is defined as the distance traveled per unit time. It tells us how fast an object is moving, but it does not include direction. Velocity, however, is a vector quantity. It is defined as displacement per unit time and includes both magnitude and direction. For example, a car moving at 20 meters per second to the north has a velocity, while a car moving at 20 meters per second without specifying direction is described by speed. Understanding these differences is essential because they allow us to describe motion accurately. Motion can also be uniform or non-uniform. In uniform motion, an object covers equal distances in equal intervals of time. In non-uniform motion, the speed or direction changes over time. Most real-world motion is non-uniform, which makes the study of motion more interesting and complex. However, motion is rarely constant. Objects often speed up, slow down, or change direction. This change in motion is described by acceleration.
Acceleration is the rate at which velocity changes with time. Since velocity includes both speed and direction, acceleration can occur in different ways. An object can accelerate if it increases its speed, decreases its speed, or changes its direction. For example, when a car speeds up, it is experiencing positive acceleration. When it slows down, it is experiencing negative acceleration, also known as deceleration. Even if an object moves at a constant speed, it can still be accelerating if its direction changes. A good example is circular motion, where an object continuously changes direction while moving at a constant speed. Acceleration is calculated by dividing the change in velocity by the time taken for that change. The SI unit of acceleration is meters per second squared. Acceleration can be uniform or non-uniform. In uniform acceleration, the velocity changes at a constant rate. For example, a freely falling object near the surface of the Earth experiences uniform acceleration due to gravity. In non-uniform acceleration, the rate of change of velocity varies over time. Understanding acceleration is extremely important because it connects motion with forces. It tells us not just how objects move, but how their motion changes under different conditions. This leads us to one of the most important topics in physics, the laws that explain how forces affect motion.
To understand how and why motion changes, we must study the relationship between force and motion. This relationship was explained by one of the greatest scientists in history, Isaac Newton. Newton's first law of motion describes the natural behavior of objects when no external force acts on them. It states that an object will remain at rest or continue to move with constant velocity in a straight line unless acted upon by an external force. This means that objects do not change their state of motion on their own. If an object is at rest, it will stay at rest. If it is moving, it will continue moving in the same direction at the same speed. This property of matter is called inertia. Inertia is the resistance of an object to any change in its state of motion. The greater the mass of an object, the greater its inertia. For example, it is easier to push a small box than a heavy one because the heavier object has more inertia. A common real-life example of inertia can be observed when a car suddenly stops. Passengers inside the car tend to move forward. This happens because their bodies were in motion and tend to remain in motion. Similarly, when a car suddenly starts moving, passengers feel pushed backward due to their inertia resisting the change from rest to motion. Newton's first law introduces a very important idea. Forces are required not to maintain motion, but to change motion. This was a revolutionary concept that changed the way scientists understood movement. While the first law explains what happens when forces are absent, the next question is, what happens when a force is applied? Newton's second law of motion explains how forces affect the motion of an object. It states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. In simple terms, this means that a larger force produces a greater acceleration, while a larger mass results in a smaller acceleration. This relationship is expressed by the equation: force equals mass multiplied by acceleration. This equation allows us to calculate how an object will move when a force is applied. For example, if you push a light object and a heavy object with the same force, the lighter object will accelerate more. Similarly, if you apply a greater force to the same object, its acceleration will increase. The SI unit of force is the Newton. 1 Newton is defined as the force required to accelerate a 1 kilogram mass by 1 meter per second squared. Newton's second law provides a quantitative way to understand motion. It connects force, mass, and acceleration in a precise mathematical relationship. This law is widely used in engineering, mechanics, and everyday applications, from designing vehicles to understanding how objects move under different forces. But forces never act alone. Whenever one object exerts a force, another force is always involved. Newton's third law of motion states that for every action, there is an equal and opposite reaction. This means that forces always occur in pairs. When one object exerts a force on another object, the second object exerts an equal force in the opposite direction on the first object. These forces are called action and reaction forces. For example, when you push against a wall, the wall pushes back against you with an equal force. When you walk, your feet push backward against the ground, and the ground pushes you forward. One of the most powerful examples of this law is a rocket launch. A rocket pushes gases downward at high speed, and in response, the gases push the rocket upward with an equal and opposite force. This is what allows rockets to move even in space, where there is no air. It is important to note that action and reaction forces act on different objects, so they do not cancel each other out. Newton's third law explains how forces interact and how motion is produced through these interactions. Together, Newton's three laws form the foundation of classical mechanics and provide a complete description of how forces affect motion. Now that we understand how forces affect motion through Newton's laws, the next step is to explore the different types of forces that exist in nature. In physics, forces can be classified into two main categories: contact forces and non-contact forces. Contact forces are forces that act only when objects are physically touching each other. Examples of contact forces include friction, tension, and the normal force. The normal force acts perpendicular to the surface of contact. For example, when a book rests on a table, the table exerts an upward normal force on the book to support its weight. Tension is another contact force that occurs when a string, rope, or cable is stretched. For instance, when a weight is hanging from a rope, the rope exerts a tension force upward. Friction is also a contact force that opposes motion between two surfaces in contact. On the other hand, non-contact forces act without physical contact between objects. One of the most important non-contact forces is gravitational force. It acts between any two masses and is responsible for objects falling toward the Earth. Another example is magnetic force, which acts between magnets and magnetic materials. There is also electrostatic force, which acts between charged particles. Understanding these different types of forces helps us analyze how objects interact in various situations. It allows us to identify which forces are acting and how they influence motion. Among all contact forces, one plays a particularly important role in everyday motion: friction. Friction is a force that opposes the relative motion between two surfaces in contact. It acts in the direction opposite to the motion or the tendency of motion. Friction is essential in our daily lives. Without friction, we would not be able to walk, drive vehicles, or even hold objects. There are three main types of friction: static friction, kinetic friction, and rolling friction. Static friction acts when an object is at rest and prevents it from starting to move. It adjusts itself to match the applied force up to a certain limit. For example, when you try to push a heavy box, it does not move immediately because static friction is resisting the motion. Once the applied force exceeds the maximum static friction, the object begins to move. At this point, kinetic friction comes into play. Kinetic friction acts on moving objects and is generally less than static friction. This is why it is easier to keep an object moving than to start moving it from rest. Rolling friction occurs when an object rolls over a surface, such as a wheel or a ball. It is much smaller than both static and kinetic friction, which is why wheels are used to reduce resistance in motion. Although friction opposes motion, it is not always undesirable. It provides the necessary grip for walking and driving. However, in machines, friction can cause energy loss in the form of heat, reducing efficiency. Understanding friction helps us control motion and design systems that either increase or reduce resistance as needed. When objects move and interact, they carry a quantity that describes their motion more completely. This quantity is called momentum. Momentum is a fundamental concept in physics that describes the motion of an object. It is defined as the product of an object's mass and its velocity. In other words, momentum depends on how much mass an object has and how fast it is moving. An object with a large mass moving at high speed has a large momentum. For example, a fast-moving truck has much greater momentum than a slow-moving bicycle. Momentum is a vector quantity, which means it has both magnitude and direction. The direction of momentum is the same as the direction of velocity. Momentum is important because it helps us understand how objects behave during interactions, especially collisions. For example, when two objects collide, their momenta change due to the forces they exert on each other. A key idea related to momentum is that it can be transferred between objects. This transfer of momentum explains many real-world phenomena, such as recoil in guns or the motion of rockets. Momentum provides a deeper understanding of motion beyond just speed and acceleration. It allows us to analyze how motion is distributed and how it changes during interactions. Momentum helps us understand motion during interactions, but an even deeper principle governs these interactions: the conservation of momentum. The law of conservation of momentum is one of the most important principles in physics. It states that in a closed system, where no external forces act, the total momentum remains constant. This means that momentum is not created or destroyed, but only transferred from one object to another. For example, consider two billiard balls colliding on a table. Before the collision, each ball has its own momentum. During the collision, forces act between the balls, causing their velocities to change. However, the total momentum of the system remains the same before and after the collision. This principle also explains the recoil of a gun. When a bullet is fired forward, the gun moves backward. The forward momentum of the bullet is balanced by the backward momentum of the gun, keeping the total momentum conserved. Another important example is rocket motion. A rocket expels gases downward at high speed, and in response, it moves upward. Even in space, where there is no air, rockets move because momentum is conserved. The law of conservation of momentum is extremely useful in analyzing collisions, explosions, and many other physical processes. It provides a powerful tool for understanding how motion is shared between interacting objects. While momentum describes motion during interactions, forces can also transfer energy when they move objects. This leads us to the concept of work. In physics, work is done when a force acts on an object and causes it to move in the direction of the force. Work connects the idea of force with the transfer of energy. If a force is applied but the object does not move, no work is done. For example, pushing a wall with all your strength does not result in work because there is no displacement. Work depends on three factors: the magnitude of the force, the displacement of the object, and the direction of the force relative to the motion. When the force and displacement are in the same direction, work is positive. When the force acts opposite to the displacement, work is negative. The SI unit of work is the joule. 1 joule of work is done when a force of 1 Newton moves an object by 1 meter in the direction of the force. Work is important because it represents the transfer of energy from one system to another. It helps us understand how energy is used to move objects and perform tasks. When work is done, energy is transferred. To understand this transfer, we must study the concept of energy itself. Energy is the ability to do work. It exists in many forms, but in mechanics, two of the most important forms are kinetic energy and potential energy. Kinetic energy is the energy possessed by an object due to its motion. Any moving object has kinetic energy. The faster an object moves, or the greater its mass, the greater its kinetic energy. For example, a fast-moving car has much more kinetic energy than a slow-moving one. Potential energy, on the other hand, is stored energy. It depends on the position or configuration of an object. One common example is gravitational potential energy. When an object is lifted above the ground, it gains potential energy due to its height. This stored energy can be converted into kinetic energy when the object falls. For example, a ball held at a height has maximum potential energy. As it falls, its potential energy decreases while its kinetic energy increases. At the lowest point, its kinetic energy is maximum. This continuous transformation between potential and kinetic energy is a fundamental concept in physics. Energy can change forms, but the total energy in a system remains conserved. Understanding energy allows us to explain a wide range of phenomena, from simple motion to complex mechanical systems. Finally, we consider not just how much work is done, but how quickly it is done. This brings us to the concept of power. Power is the rate at which work is done or energy is transferred. While work tells us how much energy is used, power tells us how fast that energy is used. For example, two people may perform the same amount of work, but the one who does it in less time has greater power. Power is calculated by dividing work by time. The SI unit of power is the watt. 1 watt is equal to 1 joule of work done per second. Power is an important concept in many practical applications. For example, engines are rated based on their power output. A more powerful engine can perform work more quickly. Electrical appliances are also rated in watts, indicating how much energy they use per second. Power helps us compare the performance of machines and systems. It completes our understanding of how forces, motion, and energy interact in physical systems.